electric field and the amount of voltage that's the voltage difference that's applied, etc., between these poles. Because I mean, at the end, it's essential for us to determine the amount of power. So the ultimate goal, probably I should mention by the end of this presentation, would be that I would be determining the amount of power that goes, that is basically supplied. Then the amount of power that is used to that goes out as radiation loss, that goes into the anode, that goes um, into the channel walls, because there is an amount of power that also is lost into the walls because of the striking of these electrons and ions to the dielectric wall. So once we get all this, we can model it in COMSOL, because we will know the amount of power to be inputted into the anode surface, into the wall surface, and the amount of radiation lost. So once we know the various powers, we can find the temperature distribution and then move on to the stresses.
Perfect.
So this was the idea that I had. And so now continuing, so the next point is the most important 2 points, which is the radial magnetic field and the axial electric field. So the radial magnetic field is basically generated by a central coil, as I said, and a set of 4 coils on the 4 corners to give the other pole. And this magnetic field is of the order of about 100 to 300 Gauss, that's about 0.1 Tesla. So these numbers again would be useful because I'll be putting them into COMSOL directly. Then the nominal, and all the numbers that I'm currently giving is based out of literature.
So this is for what is the power of the Hall thruster, because we know that the Hall thrusters, they have powers from very low to very high. So what is the power for this particular one?
Right. So last time I mentioned this is the Hall thruster that I'm trying to model.
Yes.
So this specific Hall thruster is BPT 2000, which has a thrust of 123 millinewton, specific impulse of 1765 second, and power is about 2.2, I guess. Yeah, nominal input power is a 2.2 kilowatt Hall thruster.
Yeah. Okay.
Yeah. So let's get back to this. Yeah. So the nominal input voltage is, again, generally for Hall thrusters is about 300, 400. It depends. In our case, the one that I was trying to model is 350. So the next, the few important things to note about the axial electric field. It's generated by an electric potential in the range of 150 to 800. I mean, you can apply because it depends again on the power of the Hall thruster. So in our case, the input discharge voltage, that is about 350 volts.
So for the radial magnetic field, the 300 volts is just to supply to the coils. So you have the coils have a current, and voltage on the coil is 300 volts, right? And then the axial, you have another potential difference between the cathode and the anode, which is in the range of 150 to 800 volts.
Right. So to clarify this, there are many circuits that operate in the Hall thrusters. The first circuit is the discharge circuit, which actually is supplies about 350 volts into the anode, and then it connects with the cathode and comes back. Then there's another circuit, that's the magnetic circuit, to supply current to the coils. So because the coils need current to generate the magnetic field. So that is again of the order of about 300 volts, as mentioned in the first radial magnetic fields point set. Then there is another circuit, which is the keeper electrode circuit, which is not of much importance, I figured, because it basically, the use of the keeper circuit is to ensure that the gas that comes out of the cathode and the electrons that are coming out actually really come out and go into the uh, plasma region of the Hall thruster.
Yeah, it's basically to heat the cathode so that you can have higher electron emission. So you have
Thermionic emission.
thermionic emission. Yeah, so it's a very small circuit. But the main circuit supplies, let's say, 800-volt potential between the cathode and the anode, and that is what gives the thrust, right?
Right. That 800 would be for, again, for maybe higher performance Hall thrusters. For the one that for like 2.2 kilowatt, it's the number is about 350 volt, which is the inputted discharge voltage. This 350 volt further gets divided into different regions in the plasma, which I'll describe later.
Okay.
So, and also a small point to mention, the cathode is not at 0 volts, it's at about 20 volts. So that's, yeah. Now the next point is that this creates an electric field of the order. It's again dependent on the power of the Hall thruster. It can be 2,000 volt per meter all the way to 40,000 volt per meter. So this is just the general range. The next few points to keep in mind about specifically about the anode and the cathode. The anode contains a positively charged electrode, as we know, and a gas distributor to introduce the xenon gas in the chamber. So the gas distributor is basically just a bunch of holes in the anode that introduces the gas. The size of the holes, the amount of gas that you're inputting in is generally calculated in milligrams per second, which is the mass flow rate of the xenon gas, basically. So this mass flow rate is about in the range of the order 5 to 15 milligram per second, typically in the anode. So all it does is introduces the xenon gas into the plasma.
One question I have is that this gas, the whole distribution is also designed for cooling, or it doesn't have any cooling function of the anode?
For the anode, yes, it's generally so there are different types of Hall thrusters. I remember, so last time actually I worked on only the design of the anode, where I tried to design a copper a channel, which I mean the coolant might vary, but they might send in some kind of, I mean, cooling, a kind of cooling channel within the anode to keep the anode at the right temperature.
Right.
So, but I haven't actually gone into much detail on that, because that's specifically with regard to the design of the anode. And
okay.
Yeah, we would be designing it as a whole.
Yeah. Okay.
But yes, that's done. And next in the cathode, so the cathode is generally a more complex structure, which is designed separately, which has a separate power analysis to be done, etc. Heat transfer equation can be solved for the cathode separately. So the cathode again has a dedicated gas distributor. The heater in the cathode causes thermionic emission of the electrons, and the gas distributor introduces the xenon, as we already know. And the amount of gas distributed by the cathode can typically be about 5 to 10% of the gas introduced by the anode. So, yeah, so that's pretty much on this slide. Yeah, so again, as you can see, there is an axial electric field on the right, which goes from the left to the right, and the radial magnetic field that shows in the picture. Okay, so next, a little more data about the principle. So the principle of electron confinement, which basically confines these electrons in the region of highest magnetic field, is based on the Lorentz force. So the Lorentz force is actually generated on a particle of charge q by mutually perpendicular electrical and magnetic fields. Now, as we can see, F, the force generated is q equals v cross b. So the v cross b basically gives the direction of the force, which is in the azimuthal direction. And by azimuthal, I actually mean the tangential direction. So yeah, which generates the force to drive the electrons in a circular
Yeah.
pattern. So the electrons in general move in a circular pattern, as you can see in the picture on the right. I made the round arrows,
Yeah.
but the radius in which the electrons actually rotate might be way smaller than this, than the geometry of the um, than the average diameter of the annular region that you see.
Mhm.
So the electrons might go actually, like, I mean, round and round. I mean,
Yeah.
in
Larva
circular, yeah, in a circular pattern. Yeah.
Mhm.
So that's important to note. And because we will be computing the, I mean, over the process to compute the power, we will need to compute the Larmor radius
Radius.
with which these electrons move
Mhm.
around.
Mhm.
So now, so the next point is this, this force, as in turn, causes the electron confinement in the Hall thruster as opposed to the ring cusp magnetic field in the ion thruster. So the ion thruster requires the ring cusp magnetic field for electron confinement, which results in confining the plasma. But here it's done by the Lorentz force, which keeps the electrons in that circular motion, so it doesn't let the um, plasma go out. Now the electrons move in a circular motion, giving rise to the Hall current. Okay. So the next most important point is that the radial magnetic field deflects the electrons, but not the ions. So the electrons are way lighter than the ions, and they have the next point, as you can see, is the Larmor radius. I will come to it, but they have a Larmor radius that is way less than the average diameter of this annular region that you can see. But for the ions, the Larmor radius is way higher. So the Larmor radius is basically defined as the radius in which the particle will rotate when subject to a magnetic field.
Mhm.
Um, so this radius is given basically by mv over qb. This can be simply obtained by an energy balance. If you equate the centripetal force, which is mv square by r, if you equate it to qvb, which is the Lorentz force, you can obtain the Larmor radius. Now, as you can see, data below clearly shows, so electron Larmor radius at temperatures of 25 electron volt for a radial magnetic field of 150 Gauss is about 0.13 centimeters. Uh, and on the other hand, the ion Larmor radius is really high, which is 180. So in comparison to the diameter and the geometry of this Hall thruster, the ion will just go straight. 180 is a really high radius for it to
Mhm.
actually rotate. So which is why the ions generally go from left to right. They just go straight, come out through the Hall thruster, but the electrons tend to um, go around and give this Hall current.
Mhm.
So the next, I mean, the some important thing to note is it's called the cyclotron frequency. The time period for one revolution is basically 2 pi r over the velocity. So, and we know that the Larmor radius, you can just plug it in to get the time period frequency and cyclotron frequency, omega, which is defined as qb over m. That's just another data which we might use later.
Mhm.
Now, so the um, yeah, so a few more important things for, especially for modeling. You can consider the external pressure, which is generally either in the geostationary orbit to be about 5 e to the minus 5 for external space temperature. That is,
Yeah.
that's a, I mean, it can go all the way up to 1.3 e minus 11 Pascal, but this is You can assume it to be in the range of 10 to the minus 6 to 10 to the minus 11 Pascal for modeling outer space,
Hmm.
which is generally the outside of the ion thruster.
Hmm.
Now, two more small points. There are two different types of ion thrust, the Hall thrusters available. So the first major type is known as a stationary plasma thruster. The second one is known as a thruster with an anode layer. So we will be doing modeling only for the stationary plasma thruster, which is okay. So the basic difference between these two is that, as you can see, there is a dielectric wall which actually which the plasma chamber is actually made out of. So it's a dielectric wall in the case of a stationary plasma thruster, but it's a metallic wall in the case of a thruster with anode layers. That's the biggest difference. Uh, and the stationary plasma thrusters are found to be more efficient. So hence, that's majorly used in the BPT 2000, 4000, and SPT 100. They were all stationary plasma thrusters. That's the first type. So, I mean, the point that I wanted to make is that you would be using a dielectric material to model that wall in COMSOL.
And Abhishek, the dielectric material is usually boron nitride, but you also showed one for the aluminum oxide.
Right.
Any other dielectric materials, or are these the two that are used?
There is one more called borosel. So borosel is again boron nitride, but which is with silicon dioxide.
With silicate,
So
yeah.
yeah,
Yeah, the borosilicate, the silicate makes it a little bit softer, so it probably doesn't fracture as much.
right, right.
Mm.
So yeah, so the basic thing to take out of this is that we'll be modeling the first one, stationary plasma thruster with dielectric walls.
Mm.
Then sputtering is actually might come in a later stage, but it's really important in modeling. Um, so the easiest way to explain it is so if you have these electrons and ions which are rotating and which are present at high velocities in the plasma, it is highly possible that they strike these walls of the plasma chamber, the dielectric walls that is, and so there are three different cases. So the first case is that if the velocity and the energy with which these electrons and ions strike is really less, let's say about less than 10 electron volt, then it really doesn't affect, they just get bounced back into the plasma and it really doesn't affect the wall. The second possibility is that if it is really high, let's say about it strikes with a velocity of about 10 kilo electron volt, then what happens is that these electrons, they directly get embedded into the wall, so they displace um, um, uh, they displace the structure inside, probably inside the dielectric material itself, and they get embedded. But sputtering is a phenomenon that is caused in between these two conditions.
Mm-hmm.
So once again, I'll be reading it here. If the ion kinetic energy exceeds the material's lattice displacement energy, molecules in the wall might be pushed into new positions, and it primarily occurs when the striking energy is in the range of 10 to 500 electron volt. So what happens is that when the high energy electron strikes, it tends to release another low energy, it's called a secondary electron, from the material. And so which is I mean this is the sputtering phenomena which actually decays the materials of the material that the plasma chamber is actually made out of. So I have not yet gone into an in-depth analysis, but which may be useful later if you need to analyze the structure of the wall itself. Um, Then coming to materials, primarily you have four. That's the anode, the cathode, the walls, and the propellant. That's it. So the anode is made out of stainless steel. The cathode is made out of very similar to the ion thruster. It can be made out of lanthanum hexaboride, um, or I mean porous tungsten impregnated with barium or barium oxide. But LaB6 is a primary material that's used.
For
Walls
the
of the
for
plasma
the
chamber.
for the cathode, there's also the keeper cathode, which walls, which are outside, and are those made of tungsten or molybdenum? Because the cathode, the inside has this porous tungsten impregnated with the lab 6 or barium oxide, but there's a keeper structure which is outside. Do you have information on the material?
Uh, I'm not sure. So are you asking about the hollow cathode?
Yes, yeah, right, right. The hollow
So
cathode.
actually, I think I found there seem to be different designs of this Hall thruster.
Yeah,
One is where they seem to have only the hollow cathode from the outside. That's it. There is just one cathode and one anode inside.
hmm,
So the anode is actually this ring, the anode ring it's called,
yeah,
and the cathode is the hollow cathode outside, which also acts as the neutralizer because there is a portion of electrons that goes out and
yeah.
portion of electrons that comes in into the plasma. But there are other designs which also have another cathode in the middle. Um, I believe if the hollow cathode is outside, which is like the one that's shown in this picture, there is only one cathode. In that case, the LaB6 lanthanum hexaboride will be the material for the hollow cathode. But if there are two, then
Uh, why don't you check? Maybe maybe you guys can check on that. My information is that the hollow cathode is like two cylinders inside each other, one inside, the outside. The inside one has the porous tungsten and impregnated with lab 6, but the outside is to keep, it's called a keeper structure, and it has an orifice, so the electrons go through this orifice and neutralize. But the keeper structure is important because I think there's a backflow of ions that hit the cathode, and the keeper structure gets eroded very quickly. So the reason I'm saying that is that we're trying to look for the critical elements of the design as far as materials degradation uh,
right.
is concerned. So this cathode, hollow cathode design, its lifetime, the degradation that happens, the structural and thermal performance would be kind of important to figure out.
Right. Okay. Yeah, because I think even with the thruster that I'm trying to model, there is just one cathode which is on the outside. So I never looked into
Mm,
other types which seem to have a cathode in the middle. So I mean, the other type that I'm talking about actually has a cathode right here in the middle,
mm,
right at the center line of the Hall thruster.
yeah,
So
I don't know.
yeah. Okay, so that's we have that, yeah. So
Mhm.
now, so this actually concludes. I mean, the first three slides that I wanted to just give an idea of all the numbers that are involved in the basic principle. Now, the next couple of slides, I wanted to actually go over details on the computation of the powers for each of these power losses. So input power and all these power losses. So in order to do that, we also need to design the Hall thruster, and if there is a way to verify it with the numbers that we have already got. So these are the numbers that we already have.
Yeah.
We have approximate overall dimensions and input power, thrust, specific impulse, etc. So yeah, so in this case, I mean, so first we have. Okay, so so first we have a thruster, so which has certain requirements. So the requirements are that, let's say, I just put in the same values that I found from the picture that I just showed you, the Aerojet the 2002 kilowatt thruster. So the thrust given by that is 123 millinewton. So generally, when they design a Hall thruster, the first is the requirement of thrust. So the amount of thrust that is required to actually push the payload. Let's say the requirements of the thrust is 123 millinewton. The discharge voltage is about 350 volt, and the specific impulse desired is this 1765. 1765 is again the number that I obtained from the picture of the 2 kilowatt thruster that I showed you. So now, based on these requirements, and all this analysis, Professor, actually based on the Gobel and Katz textbook, plus 2 or 3 other papers put together. So now the first thing that we do is actually compute the electron temperatures and the atom temperature. So atom temperature is basically the xenon atom temperature, which might be different from electron temperatures. And before I come into this, I would like to also say that there is a way they denote electron temperatures in electron volts rather than kelvins. It's basically because of this. Because of this thing on the top right. So temperature is given in electron volts as opposed to kelvins because generally in the Maxwellian distribution of electrons, which generally a Hall thruster follows, the amount of energy is given by this 3/2 kb times T, or in other words, if you take the 3/2 on the other side, it's 2/3 of the energy can be said to be can actually be said as temperature. So that is why they kind of say temperature in electron volts. There is a direct conversion from so 1 electron volt corresponds to about 11,605 kelvins. So there is a direct conversion, but I might be expressing temperature in electron volts from in this analysis. So so as you can see, I mean, so this is again the top, these 2 lines are basically data again from literature. So for the range of 150 volts of discharge voltage, the discharge voltage is again the input voltage basically that you give. From the range of 150 to 350 volts, it's the atom temperature are obtained are in the range of about 800 to 1000 Kelvin. And for a discharge voltage of about 150 to 900 volts, the electron temperatures are found to be in 10 to 20 electron volts. So based on this data, we can interpolate.
Just one second. So the discharge voltage, when it's 350 volt, and then you have an ion that is moving in this electric field, it will have a temperature of 1000 K, which means that the energy of the ion would be extremely low if you convert the K to electron volt. And that doesn't make sense, because you have an ion accelerated in this voltage, it has to kind of take the energy, like its energy would be comparable to the accelerating voltage, I would assume.
So this is actually for the atom itself. So that moves really slower as compared to the accelerating ions.
So these are neutrals?
Yeah, this is neutrals. Yeah, neutral.
And how do you get the temperature of the neutrals then?
No, so by atom I do mean the neutral xenon atom, which has so this is, I mean, so this is just a number that would so the temperature of the neutrals would be approximately this if the applied discharge voltage across the terminals is 350. So that's in my understanding, that's what this signifies. And then similar now to the electron volt, the one that's below is the electron temperature is about 12.6 electron volts for a discharge voltage of 350 applied voltage, that is. So I mean, generally the electron temperature are in the range of about 10 to 50 electron volts. So that's typically the range. So I mean, so again, once we know this, so this is actually kind of a reverse a calculation to do to find to kind of check on whether the diameter, etc., of the thruster that we have modeled is actually according to the one that's given by the aerojet data that I mentioned. So so I think I'll just go ahead for with the next. So there are about one, two, 3, 4, 5, 6, 9, 10. So there are about 14 points until we confirm the Larmor radius. As I mentioned, the Larmor radius needs to be in between the should be yeah. So I'll come to that later. Okay. So now the second point is for Maxwellian electrons, the ionization reaction rate is just given by this factor. So there is a lot of data in the next couple of slides, which might be either assumed data or which might be empirical relations, so which can be taken to be true. So like this is a typical example. So for example, the ionization reaction rate for, there are two cases. For the electron temperatures of less than 5 electron volt is given by this equation, and for electron temperatures of greater than 5 electron volt is given by this equation. I found these two equations at the back of the
So these formulas are from Dan Goebel's book.
electron, and yeah, that's pretty much it. So so based on this electron temperature that we got before, we can find the ionization reaction rate, which is given in units of meter cube per second. So I will come later as to how all this is used, because as of now it seems to be that just these I'm just calculating random different variables. So but they all come together in the next couple of slides. So now this is the ionization reaction rate. Now, okay. So in order to explain this, I'd like you to look at the picture on the right. So the bottom line is basically the center line of the ion thruster, and as you can see, there is a channel. So the hashed lines are basically the walls of the dielectric walls, and this actually shows just one half of the ion thruster. Now there are a couple of variables here, so let's maybe start with L. So L is basically the length of the um, uh, discharge chamber itself. Then LTH is actually the total length of the hall thruster itself. Then the next variable is DTH. DTH is the whole diameter of the hall thruster itself. Then the next variable is small d. So small d, as you can see, corresponds to the average diameter of the annular region. So the annular region actually goes around, and there is an average diameter to it. That's small d. Then small w, as you can see, is the width of the annular region, the amount of the thickness of the annular region, and then there is, okay, so now inside there are two more variables, which is Li and La. So there are two regions, which is the ionization region and the acceleration region, again in the Hall thruster. The ionization region has been marked as 1, and the acceleration region has been marked as 2. And the discharge voltage basically distributes itself in the ionization region, in the acceleration region, and ending at the cathode. So now coming back to this equation that I was trying to explain, the point number 3. So the discharge voltage can be distributed into the acceleration region, the ionization region, and the cathode voltage. The accelerate. We need to find the voltage specifically of the acceleration region itself, because we know the rest. The rest of the voltage comprises of, first, the discharge voltage, which is an input, which is 300. The cathode voltage, as I mentioned before, is about 20 volts, kept at 20, which is known. And now the next is this term that you can see, 3 plus 1 times psi of xe. So that's basically the potential of the ionization region, which is about 3 or 4 times the first ionization potential of xenon, which is 12.1. So now, in any case, so all we are concerned about is that we got to the amount of voltage that in the acceleration region is about 281.6 volts.
What is this 3 plus 1?
Oh, so 3 plus 1. So that's actually, so that's a formula. That's again an empirical formula. So 3 plus 1. So 3 is actually the number of times of which of a number of times you multiply the xenon first ionization potential to obtain the potential in the ionization region. I mean, it was really confusing to analyze this.
So you have to ionize
beginning.
xenon, and it takes 12.1 electron volt to do the ionization. But
Yeah, so 12.1 is basically the first ionized. So X
yeah,
one.
for
So
some reason you have 4 times that.
Yeah.
Mm.
So that's basic. It's actually simple. So so now, I mean, there's another independent variable which is completely unrelated, which we have found out in number 3. That's the delta V acceleration, which is 281.6.
Yeah,
It all
and
come
that,
together in the next couple of points.
yeah,
Now, the next, again, there are other independent variables, which are ion and atom velocities.
yeah.
So now the ion velocity is basically, okay, so how do I get this root of 2qvd over m? If you take everything on the other side, it turns out to be half mv square equals qv. That's the equation.
Yeah,
So
but this this v should be only the acceleration potential. It should not be 350. It should be 281.6, I think,
uh,
because it would just accelerate in this stage with 281 volt. That's my. I think it's gonna add. It's gonna change a little bit, but
yeah,
the ion velocity is 22 kilometers per second, so it
yeah.
will be
It should be in that range. Yeah,
in that range anyway.
yeah.
And then the next one is the atom, and that's what I don't understand. This is like a neutral atom, xenon atom that is thermalized,
Yeah,
and
exactly.
it just
So,
moves by itself.
yeah, so for ion velocities you use this, but for atom velocities and for the electron velocities,
Mm.
we use the, I think this, I'm not sure, but I think this comes from the Maxwellian distribution
Maxwellian
again.
distribution,
Yeah.
yeah, Maxwellian distribution
So,
at
so
a
Maxwellian
given time.
velocities are 8 kT over pi m.
Yeah, so I have a Maxwellian distribution.
Yeah, so it's now it comes together. So because now we need the atom temperature for the atom velocity, and if you see point number 5, which is electron velocity, you see it's again 8 kT over pi m, but we plug in the electron velocity. So this is where we plug in the atom mass, atom temperature, and electron mass and electron temperature.
And the idea here is that the electrons are in a collisional regime, so they collide with each other because they're confined to the magnetic field. So they become a Maxwellian gas, and that's their velocity here. And the atoms, apparently, the atoms also they have a collisional regime. I don't know if the atoms are coming from the flow that goes through the anode, maybe part of it that's not ionized. But anyway, so it's Maxwellian. And then the one that's ionized is just straight acceleration by the potential.
Right.
There's no collision.
Yeah. So I mean, so to make it clear, there are actually three different velocities that we have here. As you can see, the velocity of the atom itself is low because it's the xenon atom, which is not. I mean, that's not the one that's accelerating, but the VI, which is the first
Mm.
one, is what is really high, which is about 22 kilometers per second,
Yeah.
and which is again typically of uh, of the order of the exit velocity, because the exit velocities of these ions are about 30 kilometer per second, in that range.
Yeah.
So yeah, and the electron velocity was again will be high. So yeah,
Mm.
but that was not used much later. But in any case, so next moving on, we have so the goal of this point number 6 is actually to obtain m dot a, m dot c, and the total m dot. So now m dot a is basically the amount of mass flow rate in milligrams per second of xenon gas coming out through the anode, and the m dot c is obviously the other one, that's the cathode. We know an interdependent relationship between them, because the amount from the cathode is about 5 to 10% that of the anode. So if we just know one, we know the other. But how do we get to finding the total mass flow rate that's actually required to get that amount of thrust?
Mhm.
So that would be the sum of the anode and the cathode mass flow rates.
Okay.
So the thrust is actually m dot v. So that's a very common formula. So m dot v, and v exit velocity is given by the ISP times g. So ISP is the specific impulse times the g, which is 9.81. So I just equated the thrust, which is 123, which I've assumed in the beginning, equal to m dot times ISPG. The ISP is also known, which is the specific impulse 1765. G is known. So we can easily find the amount of mass flow rate that's required in the thruster as a whole. And once we know that, we just distribute it between the anode and the cathode. So which is m dot through the anode plus m dot anode plus 10% of m dot anode, which comes out through the cathode. So now we know the mass flow rates. Now, the next is actually to find the yeah. So now actually it comes to finding the diameter of this the mean diameter of this annular region, which actually we start to model the geometry of the ion cluster. So how do we get the diameter? So there is again an empirical relation. So which actually equates. I mean, it's a relationship between the diameter, mean diameter, the amount of mass flow rate coming out through the anode, the mass of the xenon atom, and the ion and atom velocities of xenon, and the sigma IVE, which, as I mentioned before in the previous slide, is the ion reaction rate. So I'm not sure again how the empirical relation comes out, but the diameter of the Hall thruster is again, this is how it's estimated to be about 12 centimeter. Now I come,
Sorry, Abishek, but by diameter you mean radius in this case? Because we're looking at half the Hall thruster.
no. Actually, I think it's the diameter. But I in the picture, in the diagram on the right, I marked D as. I mean, that looks like a radius, but it's the diameter. So it's the whole diameter. So
Okay.
so now so based on this initial diameter, there is a whole bunch of correlations with which they are proportional correlations, and they are all dependent on this average diameter of the annular region. So like, I mean, so this next couple of lines that you can see, other dimensions, you have W, which is the thickness of the thickness, or I would probably call it, I mean, I don't know, the yeah, the I mean the amount of gap, the gap between the inner and outer.
The channel width, yeah.
Yeah,
Channel.
the channel width. Yeah. So then you have the actual thickness of the wall, then the channel length, then you have the diameter, the overall diameter of the thruster, and the length of the thruster. They are all interdependent on these other dimensions. And so based on this computations, uh, whose input was just the thrust, the ISP, and the discharge voltage, I obtained these outputs, which are the dimensions of the Hall thruster. I compared this to the data that's given here, and it's in similar range. So as you can see, the thrust inputted is 123, specific impulse is 1765. Based on these numbers, we computed this. So the envelope dimensions are basically the overall dimensions of the thruster, which is like 15 centimeter by 17 by 22 centimeter.
Mm.
So this specifically would be in the range of, in this range that you can see here, the diameter of the thruster comes out to 24, the length comes out to about 12. So this is how we at least characterize how we designed the Hall thruster. So this was the first step.
So the idea for the idea for the design is that you are given a specific impulse, 1765 as input, and you are given a potential, a discharge potential. So from the discharge potential, you get the acceleration potential, and from that you get the ion velocity, like 22 kilometers per second. And from the ion velocity, you match it with the specific impulse, then you get the mass flow rate. So you have to have a certain mass flow rate, like 7 milligram per second. And from that, what I don't understand is this formula. So in the mass flow rate, you have to have some reactions inside the chamber, apparently, to to maybe ionize most of that mass. I guess this must be the ionization reaction rate. So you ionize it to that level. So that needs a little bit of understanding. But basically, the idea is that you have to ionize it so you get the diameter to contain that gas and maintain it in this ionized form. And then you have like interdependent relationships with that diameter to size the Hall thruster, right?
So yeah, that's actually, yeah, that's the entire crux of the dimensioning the Hall thruster. And a few more points. Number one is again back to this relation on the top right as to how I obtained the diameter directly from the mass flow rate. Is again, it was an empirical relation. I didn't want to go into it in too much detail because my goal was more to determine the diameter and go ahead finding the powers. So I figured maybe I just assumed that to be right.
Yeah.
And the second point is,
where did you get this formula, Abhishek?
okay, so again, this was, wait, I'm not sure if this was specifically from the Gobel and Katz textbook, but it's either from that textbook or one among these 3 or 4 papers that I referred. I'll be uploading them to our shared
Okay.
So it's, yeah. So and yeah, point number 2 is this thrust, what you can find right here, the 7.104 milligram per second, that we derived specifically for this thruster is actually again right, because the amount of nominal flow rate that they give is about 7.1.
Yeah.
So basically those formulas have been used and all that to design back this Hall thruster. So this was actually just a direct picture that I found online, but it seems to at least correspond to the values seem to correspond. So now the next phase is actually this is the yeah. So now okay, so now again there might be a bunch of variables which might end up all coming together to determine the electric field that's required to be. So because based on the amount of thrust that you need to decide the amount of electric field that you need to give, the amount of magnetic field that you need to give. And all this would be actually inputs in our console model. So we'll be computing the amount of electric field, the magnetic field, and we can do the console analysis directly, do the heat transfer and structural analysis directly. So that's the idea of this second phase. Now going back to point 9. So number 9, we have Im dot. So Im dot is basically the current um, that actually goes through the anode. So the current going through the anode actually can be, so there are electrons that go into the anode. So the current can be assumed as coming out of the anode. So this current, or the ions that come out of the anode, is basically this ion. But that can be distributed into these ions that actually give the thrust, that come out through the Hall cluster, and the ions that go and hit the wall. So because as we discussed, there are certain ions that go and hit the wall, which is a loss. But there are certain ions that actually come out of the ion thruster, which is the beam current, basically. So there is a beam, and that's the beam current. So in simple words, the total not number of ions, the total current coming out of the anode is equal to the amount of current that hits the walls and goes as a loss, plus the amount of current that's coming out of the ion cluster. Now, this current that I'm first trying to say, the number 9, is basically the total current coming out of the anode. Again, this E m dot A over m was again found through this was again through Goebel and Katz, I believe, but I was not able to deduce as to why E m dot A over m. We know what each of these mean. E is the charge of an electron, m dot A is the mass flow rate of through the anode, and capital M is basically the mass of the xenon atom itself.
I would guess that, like you have gas going through these holes that has a flow rate m dot A, and then each atom, if it is ionized, singly ionized, then it will have a charge, and the charge will be the charge of an electron, because just when the atom loses an electron, then it becomes positively charged, and its Q is the same as an electron charge, which is 1.6 times 10 minus 18. So you have each atom coming out now as an ion, and it has a charge of Q of 1.6 minus 19. And that is the current that comes out if you divide it by the mass of each atom. Because the mass flow rate, if you divide it by the mass of each atom, it gives you the charge flow rate.
Charge flow rate. Oh, okay.
The charge flow rate is multiplied by the amount of charges carried by each one, and that gives you the current.
Yeah, actually, yeah, the unit wise it's actually right, because so the mass flow rate over the mass gives actually the unit would be 1 over time, and the charge over time is actually the current. Yeah, so that's, yeah. So again, now over this again, the next 1 or 2 slides, there will be a couple of assumptions, and all these assumptions are again either based on Goebel and Katz, the textbook, or from the papers that I saw. A typical example is this next one. The discharge current, as you can see, the next step is 1.3 times the Im. So again, I'm not sure how this comes in, but the amount of current that's through the anode so the discharge current, they say, is 1.3 times the current going through the anode. I wasn't quite sure about this, because shouldn't the discharge current, the discharge voltage is actually connected to the anode and cathode. Shouldn't it be the same? But I wasn't sure, but this is what the text said. So we obtained the discharge current to be 6 point something amps. Now, I went back to do checks. So now which checks out with, okay, so we can do a back check, because we know the power input is basically equals VI. So now the input power we know from that picture, this picture it's a 2.2 kilowatt thruster. So it's about 2,200 watts. So now 2,200 watts equals VI, out of which we know V, which is 350 volts, and which gives an I of about 6.3 amps. So I concluded that the discharge current calculated must be about right. So That's
I guess there's also a certain amount of gas coming from the cathode that adds to more current, right, to the anode. So you have a mass flow rate through the anode,
oh, yeah,
and you have another mass coming from the cathode.
right.
So maybe that explains the difference. I don't know.
Right. No, that's probably true because you need to take into account the ions that are going into the, yeah, cathode too. That's true.
Mhm. But in a
That's
simple
actually
way,
right. So because the
in a
ions
simple way,
are
you look at the whole thruster as a wire, and you have 2200 watts power dissipated in that wire, and the current going through it is 6.3 amps, and the voltage is 350 volts.
right.
That's the
Yeah.
way to think about
Because the amount, so let's say the ions that are coming out of the Hall thruster, there are two possibilities. Either those ions recombine with the electrons from the cathode to give the whole atom, because it needs to be neutrals which are sent out. Only then the body itself doesn't get a charge, which is why you have the neutralizer cathode. So there
Yeah,
is one possibility is it goes out as neutrals, or the other possibilities is this ion also somehow goes into the cathode. A very small portion can possibly go into the cathode.
yeah. That's what I was saying is that the keeper, that some of the ions will have to, like the ions coming out, and then they would want to go to the cathode just
Right,
naturally because they're pulled out. They want to go to the cathode. So the
right,
cathode will shoot electrons towards them, and the
right,
electrons will neutralize it. Once they're neutral, they are not affected by the electric field. So they can
right,
just kind of move in free space.
right,
They do not charge. But then a fraction will escape, and then it will hit the cathode.
right,
And when they hit the cathode, they erode it, and they get very high heat flux on that cathode surface.
right, right. Um, yeah. So that's so now we obtain the discharge current. That okay, that seems to check out. Now next is the some calculations that are essential to find. As I mentioned earlier, there is, if there is an X current coming out of the anode, it gets split into the ions that hit the wall. So there is a current that actually hits the wall and goes as a loss, and the amount of current that actually gives the thrust, and that really comes out as ions out of the ion thruster. So that's the aim of this point number 10. So
Mm.
now, as we can see, the cathode efficiency is given by m dot A over m. So that's again, so m dot A is the amount of mass flow rate through the anode divided by total mass flow rate is actually the cathode efficiency. I'm not sure why, but that's again the formula. Now for jet power, um, yeah, so jet power is again given by P square over 2 ma. So this is actually a simple correlation. This can be computed from uh, um, by actually combining two different equations. So one is, we know that the thrust is m dot v, right? And we also know that the jet power is basically half m dot v square, because it's kinetic energy of the ions coming out. So half mv square is the kinetic energy, and half m dot v square would be the power. So if we combine half m dot v square, which is the jet power, with the thrust equation, we actually obtain this equation that you can see here, which is jet power equals, in terms of thrust, the jet power in terms of thrust. So now all I do is I plug in the cathode efficiency, and I get a jet power of, let's say, what it's 1 kilowatt. And then the acceleration power is, again, there's another, I mean, there's an in-depth concept that goes into this. Why is it jet power divided by gamma? Gamma is a zero point 0.9, is a factor that actually comes from the fact that you need to take into account xenon to xenon plus, as well as xenon to xenon 2 plus. So that's the factor gamma, which I haven't elaborated upon. But we are concerned with the net acceleration power, which is which is about 1 kilowatt, 1.18 kilowatt. Kilowatt.
Oh,
Now,
sorry. So you're saying the extra 10% of power is coming from the heavy ions, like the heavy isotopes of xenon? Am I?
yeah, exactly. So like, I mean, um, oh yeah, if you put it that way, yes. So because xenon, so we have taken into account only Xe plus. So yeah, exactly. So that's about 10%, right? Which is about 118 watt in this case.
Well, the xenon, it doesn't have isotopes, Dylan. The xenon is the same, but it can be singly charged or doubly
Oh,
charged.
doubly, yeah.
If you lose one electron, then it will have one charge. And then if you lose two electrons, then it will have twice the charge. If it has twice the charge, then it will move twice as fast because it's pulled by the electric field faster. So
Okay.
that's the
Thank you.
difference.
Yeah, thanks for you.
Yeah. So now, I mean, so now it all comes down to this next crux equation that's pretty easy to understand. So the net acceleration power, like power is again equals VI. Is so net acceleration power would be what? Would be the delta V axle. So now we actually come to the delta V axle thing, the variable that we obtained in point number 3, back in the slide in point 3. We said that the amount of voltage to which the ions accelerate, that's the acceleration layer voltage, is about 281.6 volts. So we plug in that voltage, which is responsible for accelerating these ions, times the current. And the current, as I mentioned again, is not the total current coming out of the anode. It's the current coming out of the anode minus the amount that's lost into the wall. So if we just plug in everything into this, the only unknown variable is actually the current that's going into the wall, which we find out to be half an amp. So that's what we obtain um, for this. And yeah, so so now the next again independent variable that will come all together is the length of acceleration layer. So length of acceleration layer is basically, let's say you have the acceleration occurs between this potential and this potential, which is the acceleration layer. We found out that uh, uh, we need to find the length of this layer in order to find the electric field. So the length of this layer again comes from a bunch of empirical correlations, which comes out to be about 1.8 centimeter, which is actually this point number 11. Now now finally it's possible to obtain the electric field, which is in units of volt per meter. So the volt per meter electric field would be given by the the exact delta through which the ions are accelerated. That's that voltage divided by this length of acceleration layer, which comes out to be about 15 kilovolt per meter. So that is the electric field that is required to for this particular model of thruster, which has been designed to give output of so much thrust. So that's what it actually means.
Mm-hmm.
Now, the magnetic field can similarly be obtained by another empirical correlation, which gives the maximum magnetic field as about 116 Gauss. Now, I mean, it's still hard to see whether all this is actually falling into the right design. In order to see if it's the right design, it's the Larmor radius verification, which is point number 14. I described Larmor radius before in this slide. So to just for recap again, so this Larmor radius is given by mv over qb, and this Larmor radius is again the radius with which these electrons or the ions rotate and revolve, sorry. um, uh, when they are subject to a magnetic field. And once again, the most important point is that the electrons should not get deflected by the magnetic field. Only the ions should get, no, the electrons should get deflected and the ions should not get deflected by the magnetic field. Um, so in order to prove this, we need to ensure that the actual diameter of your thruster is such that the Larmor radius of the electrons are really small as compared to this diameter, and the Larmor radius of the ions are really large as compared to this diameter. So if we prove this right here, so the ion Larmor radius is given by mv over qb. So velocity is the electric field over the magnetic field. We find that it's so much, and electron Larmor radius comes out to be so much, which actually satisfies the width of the, I mean, the width or the diameter, you can say, of the uh, thruster that we found out in the previous steps.
Okay.
So this needs to check out in order for the thruster to actually have electron confinement.
Yeah, so this is really a very good analysis of the power and the currents and the voltage everywhere and the mass flow rate. So we have a pretty good idea. I think what we want to do is move from here to the thermal loading.
To the thermal load, yes. So yeah, so it's just, so the next that's this pretty much I think these are the two last. Yeah, this pretty much concludes it. So now the final step is actually this kind of, it's a power balance that would help us to confirm that everything is okay, and which will also help us to individually find all these powers so that we can input them as boundary conditions to our console model. So now, now to explain what all these are. So the first is the discharge. PD equals sum of all this. So PD is the discharge power that we actually input. Now this gets divided into, first, the beam power, which is actually the useful power that's actually coming out.
Right.
Then PW, which is the power to the channel walls, because there is an amount of current that hits the walls, the power to the channel walls. Now PA, the power to the anode, due to the electron collection, because electrons are collected in the, into the anode. And the PR, which is the radiative power loss, which is actually not much, which is sometimes ignored too, because it's less as compared to the overall power. And P ion, which is the power required to produce the ions. The only one that I'm not quite sure about is the power required to produce the ions, which I was not able to understand physically what it exactly means, but
I think, Abhishek, it's a power because each atom comes out as a neutral, and then you have to ionize it. So you have to spend 12.1 electron volt to remove an electron, and that's a factor 4. I don't know where it came from, but that's basically the power that is used to ionize the gas.
Okay. So so it's basic, yeah. So to ionize either from Xe to Xe plus or to Xe2 plus. Let's say.
Exactly, and then you multiply this by the mass flow rate, and you convert it to a current, and the current times 12.1 electron volt times 4, which I don't know what 4 for, but that should be the power to make the neutral atoms become ionized.
Okay.
So you have to spend that. It's like a price we have to pay to create ions and electrons.
Right. So now, as you can see, the final stage is, again, there is some empirical relations involved, some assumptions, but so the beam power is basically IB times VB, which can be easily obtained from. So actually, IB and VB are obtained from the discharge. So IB and VB are the beam current and the beam voltage, which is the net useful output. And through the means of an efficiency, that's the current efficiency and voltage. It's called current ionization efficiency, voltage ionization efficiency. I guess I'm not sure. So through means of that, we can relate it to the input. That's VD. That's the discharge voltage and the discharge current. So, I mean, based on that, it's easy to calculate beam power. Then the power loss to the channels is the biggest, generally is the biggest power loss in any Hall thruster. So that's about 473 watt. So these are the numbers that I have not yet been able to confirm, that will probably be confirmed if I give inputs to COMSOL and try to do the analysis to see if I get the right numbers. So now 473 seems
So
to
this
be
is the power going to the dielectric walls, and this will
yes,
be like in the form of electron impact or
ion impact.
ion impact or what?
So it's a power lost because of electron or ion impact, because you have um, so again, so
Because you have this Larmor radius, and then some of them will strike the walls, I guess, before they get out.
yeah, but the ion impact typically is very less as compared to the electron impact, because as I mentioned earlier, the Larmor radius of the ion is very large, so it tends to just come out straight.
So it's
But
mainly electrons.
yeah, but it's primarily would be electron impacts.
Mm.
So, but I think the ion impacts are also included in this equation.
Mm.
So that's the power that's lost to the channel walls. Now next, the power to the anode is PA, which is 2 TeV. So again, this is so I did not want to go in depth into these equations, but I mean, as in a very brief way, if we assume this empirical relation 2 times TeV over 2 TeV Im to be right, then that's the power to the anode. Oh, on the top right, actually in the right hand side page, I have computed the VB and the IB. So VB is 330 and IB is 4.2. And then from that, I try to calculate an efficiency, which gives the voltage efficiency as about 0.95 and the current efficiency as 0.68 or 0.7, which is also in the right ballpark, because that's what the texts said. And other than that, the radiative power loss and the power to produce ions are generally really less. So,
Question, Abishek. I know you're trying to be brief over this, but does that seem reasonable that like a third of the beam power equivalently is being lost for the power channel walls? Am I interpreting that correctly? That
yeah. So so that's what. So exactly. So it's about okay. So I think there are a few things. So the first point is it's a 2.2 kilowatt thruster. So the amount of power inputted itself is not more than 2,200 watt, out of which we are able to extract 1386 or 1400 watts out of it.
So that's the efficiency. The efficiency is 1386 divided by 2000, something like 40% efficiency.
Yeah, so our Hall thrusters operate at about 50% overall efficiency.
Yeah, and the rest is losses of various.
Right.
The main one is the channel to the walls, right?
Right.
Mm-hmm.
Yeah.
okay.
And that you convert it to heat, like it'll be a heat flux. So if we have the dimensions of the channels, we can compute the average heat flux from, say, 473 divided by the area. That can give us an average value of the heat flux.
Right.
And that seems to be kind of small, right? Because what would be your guess for the area of the channels? Seems like it should be less than 0.1 meter square. Sure.
Yeah, so I think the typical heat flux for Hall thrusters is, I mean, like for the turbine blade, it was really high, but I don't think, I'm not sure how, I don't have a number on the heat flux for a Hall thruster.
Mm-hmm. Well, from your calculation here, if you have the wall power and you divide it by the surface area of the wall.
I think surface area of the wall, by the way, is like about 90 square centimeters.
Okay. So let's say 100. So 500 divided by 100. So it's a 5 watts per centimeter square. So per meter,
meter square.
be 10 to the 5 watts. So 5 times 10 to the minus 6 divided by 10 minus 4.
500,000.
So
That's
0.05
500.
would be 0.05 megawatt per meter square. Very, very low. Like we have to cool something like, let's say 0.1 megawatt per meter square and above. So this will be 0.05.
Megawatts.
So you probably don't, that's why you don't have to cool it, the walls, I guess.
So is it so about 50 kilowatts per meter square, right?
Yeah, 50 kilowatts. Yeah, 50 kilowatts.
50 kilowatt per meter square, right?
Okay.
So
Yeah,
50
I need to check if that's right, actually. I'm not sure if that's the right number.
Yeah. That's why if you divide by, if you make it megawatt, so it would be 0.05 megawatt per meter square. So according to the graphs that we have, the cooling starts at about, let's say 0.1, 0.2, then you have to do something, you know. And maybe that's why you don't have to do anything. You just kind of, I don't know if you have radiative cooling, how hot does it get, you know, in this case, where is the heat dissipated? That would be kind of the issue.
Right.
And what happens if you go to higher power Hall thrusters, you know, how do they cool it? So
Right.
that's kind of what we are facing here.
Right.
Okay.
So yeah, so that's pretty much. So now I mean from here there's one console model that I did, but I'm not yet fully done. So I need to further up on that. And so once we have the powers, whether it's 2D or whether it's 3D, it's easy to give. If it's 2D, you give it. I mean, you give the powers to a particular. I mean, face line. Like if it's 3D, you give it to a 3D surface. So it would be easy to couple the heat transfer and structural mechanics modules after this.
Right.
That's
So if we I think what you want to do is type, you know, these equations that you have and some references. So we can start the beginning of a report on the Hall thruster design. And this documents, you know, all of the steps that you've gone through, the sizing and the power distribution. And then our next step is to do modeling, I think thermostructural modeling. And the interest would be in maybe three components. One is the dielectric channels themselves. And here you got some power, you know, like 500 watts going there. What is the temperature rise and what is the stress that is to be expected, especially if we consider, you know, if they have startup shutdown of the Hall thruster. Is it a continuous operation, or is it, you know, they turn it on or off with that power going to the channels? So there's like one design problem, thermostructural design problem would be the design of the dielectric channels themselves, you know, from that number that you got.
right.
So that's one direction. And then the second is the design of the anode, and it doesn't seem to be a critical component from what you have here. But again, you know, we can look at it and see if what temperature rise we would have. It seems like they have certain channels to flow some gas to cool it, or maybe it's cooled enough by the flow of the gas inside. But at least we understand, you know, what is the thermostructural conditions with that. If it is not critical, then we just kind of leave it aside and
The cathode analysis is, I think it's pretty good. I mean, in the last time Zoom meeting, I mentioned certain equations for the cathode analysis, which is, I mean, because in that you can, I think it's possible to do a thermal balance sort of.
Yeah, and then the cathode. So I would say, like, you know, the report that we have on the design would be the overall sizing, which you've gone through very nicely here with references, and then the CAD model to reproduce this Aerojet configuration, and then now design of critical components. Component one would be the dielectric channels, and then component two would be the cathode, the hollow cathode, in more detail.
Right.
Component three would be the anode, just to kind of to see where things are. That's kind of the structure that I would like to see in this design report between you and Dylan.
Okay.
Good question, Abishek. Do you have
Yep.
any of those equations in like a MATLAB code that can be modified quickly?
Oh no, not yet. I mean, because I think I can do this, because this seems to be like an entire it's like a procedure with which the design can be done. But yeah, that would be easier to. I can put them into a
Actually,
code.
this is a good way, like if you do
Yeah.
a hand calculation for one case, which is the
Right.
this 2000 watt thruster,
Right.
and then you can just program in MATLAB, and then if you want to go to investigate what happens at high powers, if we go to higher thrust or we go to higher power, do we have difficult thermal structural problems, and where are these? So this is our concern, is that we want to push the envelope, these thrusters, the operating, they say that the lifetime is 6,000 hours. We want to figure out why is 6,000 hours.
Right.
Maybe it is due to some thermal structural on-off time on the cracking on the dielectric, or it could be due to the erosion of the cathode keeper, or the cathode itself is not functioning very well. So at the end of the report, we're going to say the lifetime is determined by either the cathode or by the dielectric structure.
Yeah, yeah.
And then after that, we say, okay, we have a MATLAB code, then we can go to higher power designs for the future. Do you want to go to, instead of 2 kilowatt, you want to go to like 200 kilowatt, what kinds of the problems are going to be exaggerated? Where are the thermal structural problems going to be? So this is what we wanted to do actually with this design.
Okay. Yeah.
Very good. Very good. Okay.
And I mean, so this, I'll elaborate on this a little more, because I think even the dimensions on this are wrong. So this actually shows the basic, I mean, a very basic Hall thruster, half Hall thruster, sorry. So the leftmost corner is a 0, 0. That's so this is like one half of the annular region, as you can see. So the left magnet is a north and the right magnet is a south. But pretty much, I think because the dimensions point on the x-axis, it goes up to 0.05 meter, which is 55 centimeters. No, which is yeah, the dimensions are. I didn't get the dimensions right on this yet, but I was, yeah.
So this is just the magnetic field analysis for the Hall thruster.
Yeah, but it uses permanent magnets instead of the coil. So I thought that maybe you should use the coil, right? Because that's more realistic. But in a
yeah, but maybe
analysis, I still have not figured out how.
Yeah, but Abhishek, I think the magnetic design is probably not like so significant for us. I think we would want to just continue what you did and then start looking at the thermal structural design, because to really have a complete kind of model that is multi-physics, you have to start from magnetics, and the magnetics are coupled to the plasma, and the plasma go through your numbers, but more detail to give all of the, the power distribution, and then you do thermal and structural.
Yeah.
But I would say we want to just short circuit that, and then go from your power analysis. You can make nice diagrams for how the power is split. And then once that is determined, then we take that as boundary conditions thermal boundary conditions to analyze the anode, the channel, and the cathode.
Right. That was I think that was pretty much my idea too, because like if we have different individual analysis. So the first is like the preliminary calculations to
Yes.
design, which is what I mentioned in the presentation today, and then we have the power calculations, and
Yeah.
then we have an independent magnetic field simulation, which might not be linked in like coupled to the thermal or structural, because I mean, we just show the pattern of magnetic field lines.
That's it. Yeah, you're not gonna do anything. Just show the pattern. So I think, like, you know what Dylan was saying. If you, let's say, structure a MATLAB code that has part of it would be physics parameters, which is Larmor radius and ionization potential input parameters, and then part is the power electric circuits, basically. You know, what is the discharge voltage, what is the currents going through, so circuit analysis basically and power. And then the last part is a power distribution, and then the final result is heat loading coming to the components. And then that can, we change something in the top, then we can figure out what is the heat loading, what is the sizing, what are all of these things, and then we use this as input to do thermostructural modeling.
Right.
And Abishek, I'm happy to help with that.
Yeah, that would be good for you, Dylan, to actually design that. It's like a design project where you have a MATLAB that actually has, you know, if you go back to the Aerojet specs. So the Aerojet specs have design specs, and they have, you know, thrust requirements and efficiency. So like this here, so performance and design specs. So that would be the constraints that we put in the MATLAB from the beginning.
Right.
From there, we go physics kind of equations, and then we go electric circuit equations, and then we go power equations, and then we go thermal loading output. So if we change, you know, from Aerojet to something that is designed at University of Michigan, let's say they're designing a 200 kilowatt instead of 22 kilowatt, then we will see the impact right away, and then we could do the modeling from our side.
Right. Correct.
Okay, sounds good. Sounds good. We made some progress today. All right, so I think if you guys work on that, that would be great. Like two things. Number one is that documentation. That's your thing, Abishek, is to write like a report, and it has the references and the hand calculations that you did. And the second is designing this MATLAB module. It shouldn't be too difficult, and then getting the input to the thermostructural calculations. And then you're going to have to do the first model I suggest would be the channel walls.
Okay.
So let's focus on that.
Okay.
And then after we finish that, then we go to the cathode, the hollow cathode, and then finally we do the anode just for our understanding.
Yeah. We could actually, separate the whole thing out into three independent models.
Exactly.
It's easy to even 3D model the channel walls, because it's just a wall with the anode at the bottom. So yeah, that should be simple. Yeah.
Very nice, very nice. Okay, so we have a good plan now.
Yes.
All right, so I guess you have more time now, Abishek. You said that you can put more time into that.
Yeah, I do actually. I also, I mean, I had a question about, I mean, so if in case it extends beyond a month, would it be possible that I could, I mean, because go ahead a little further, because I want to somehow see it through, and because I do, I mean, at least in the last 2 weeks, I wasn't spending much time on this, but I will compensate more on the next coming couple of weeks now.
Yeah, no, I would authorize that, you know, provided that you kind of put the time. And I think if we focus on having a design report and a design process between MATLAB and COMSOL for the Hall thruster, these components, I think that will be a good outcome for the effort. So if you put more effort, that would be great. And then I think Dylan might have a little bit more time. He finishes midterms, and he would work with you on the thermal structural part.
Yeah, absolutely.
Okay. All right, sounds good. Sounds good. Yeah, very good.
I'm sorry, the meeting went more than
Oh, that's okay. So I think we made a lot of progress today, and we have more understanding as a group. So let's go at it for a couple more weeks, and then I'll call for another meeting once we have some more progress.
Okay.
Sounds great.
Sounds good. So we'll see you guys and have a good weekend.